Hi, I'm Ilya, and today I'm going to tell you about kubenetmon, which is a tool we built at ClickHouse Cloud to monitor our data transfer in the cloud. I work an engineer in ClickHouse, and ClickHouse is a very fast columnar analytical database, and we run it in our company in GCP, Azure, and AWS. We do open source development for the database, and in the cloud we build tons of cool features such as compute separation, auto scaling, and support for special table engines that store data in the blob storage. And what I want to tell you about is the story of how it is very difficult sometimes to understand your data transfer in the cloud, and at the same time it's very important, especially for data-intensive applications that move a lot of data back and forth. And it's important because obviously the cloud providers, they charge you a lot for the data transfer. So there's many different categories, such as for net gateway, for outbound connections, there's load balancers, there's different categories such as cross-region traffic, et cetera, that are very hard to understand, especially when you're running a multi-tenant infrastructure. So what I'll tell you about is what we needed to get from network observability, what kind of tooling we already had, and what was there in the market for us, how we compared these tools, and how none of them really worked perfectly for us. And we decided to build something very technically cool, which is called kubenetmon. And we open sourced it and wrote a blog post about it. So to start with our needs, I'm going to tell you a little bit about our network topology. So in the center of the picture here is ClickHouse server. These are replicas that we run for our customers, and they can be co-located on different nodes with other customers as well. They can be dedicated. There's many different scenarios here. Typically, all starts with a customer connecting to their own ClickHouse instance, and they do it by opening an inbound connection. It's inbound from our perspective. This connection goes through the network load balancer, through a component that is our proxy. We're on Istio. It's not pictured here, and landing in a ClickHouse server. Obviously, connections are bidirectional, so for this inbound connection, you have both ingress and egress paths. Now, ClickHouse itself might also open connections. It might download some data either from S3 in the same cloud, or maybe something from the public internet, in which case it will go through that gateway. And these connections we call outbound from our perspective. And again, they have two directions, ingress and egress. And it would be good to understand, to be able to capture all of these views, and additionally also to capture east-west traffic. That's not shown here because we run many replicas. They talk to each other. There's keepers running for coordination. There is also supplementary services that we run ourselves, and getting a complete view would be very good. So we framed our high-level requirements like this. It would be good to be able to address the need for forensics, a record, some sort of artifact about what connections are being open, so that when we have an incident, there is a node that's overloaded, or we want to be able to get larger nodes in the future, and we need to know how much throughput they should be able to sustain. We want to have this forensical capability. Then we want to have metering. Once we know individual connections, we want to know which workloads they're attributed to, which customers, what exactly are they doing. And then there is accounting, which is about larger rollups, like this particular business use case, such as supporting cross-regional backups, cost us this much in the second quarter last year, for example. So to support these, we went through what we already had in terms of network observability. Let's go through the list here. So first of all, we already have Istio proxy, which collects connection records that are called access log. And we have tons of information there: duration, remote addresses, local addresses. We know who we're connecting to. We know the byte and packet throughput. But unfortunately, there's two issues here. First of all, the proxy is located in the front of our architecture, so it doesn't see any outbound connections or anything east-west. And secondly, unfortunately, it's logging. We're inserting here one record per connection once it's closed. So if a connection is open for 24 hours, we're not going to get any insight into how it evolved, were there any spikes, and we'll only get any data quite late. So it didn't quite work for us. Then we also have system tables in ClickHouse. ClickHouse system tables are tables that ship always in every ClickHouse instance, and they have a lot of very useful information related to how ClickHouse is running. In particular, the most famous one is query log, where you have information about every individual query. And one of the columns is profile events, which gives you information about the performance of the query. And there is some network related information here. There is also different metrics ClickHouse provides in its system metrics table, such as for the number of connections. This is not exactly enough because first of all, the granularity here is per query, whereas we want something more workload based and per second or per minute resolution. And secondly, ClickHouse is a higher level user space application, so it doesn't necessarily know about all traffic that it's sending, where exactly is it going. And also obviously it doesn't have visibility to traffic that's not related to ClickHouse workload itself. So it didn't quite work for us either. Then there are Node Explorer metrics. Many people run Node Explorer. These are great, very useful, but unfortunately, fundamentally, they come from the Linux's metrics on network devices. So they don't tell you anything about which IPs were talking to which IPs, which ports were involved, how many connections there were, and obviously nothing about the individual workloads. The best you can tell is which node or maybe interface this could be attributed to. And then there's cloud provider flow logs. The issue with them is number one, you need to pay for them. And our goal here is to hopefully shed the costs. Number two is it's a bit of a patchwork between different providers. They all have different advantages and different disadvantages, missing features. And actually the union of things all the cloud providers are missing together is basically like rebuilding the entire system from scratch if you want to patch them up together. So this didn't really work for us either. Upon reflecting on these needs, we were able to articulate our requirements a little bit more concretely. So forensics, if you remember, so now we understand we want to have a clear reference point to observe from. We want to have a mental model where we're getting the data from. So for example, Istio is not in the right point of reference. Then we want to have information about connections. So L4 or L3 data here and not just business categories. Okay. We want to know about bytes and packets and not just dollars, which is what a lot of observability tools focused on FinOps give us. And we want to have rates. I don't want to know how much traffic we send per month. I want to know how much we're sending right now per second. And then finally, to that for metering, we want to attribute it to pod names, instance names, spaces, everything like that, sampling points that we're getting data from multiple places. And then finally, for our FinOps team, we want to roll this up into relevant categories and periods and hand it over to them or other analysts. So again, to go through the list of existing tools, just to sum them up, here's what we have. Proxy, access log, their blind spots, and it's connection-oriented. ClickHouse, very useful for query debugging, but as a downside, query level resolution is not what we need. VPC flow logs, they're just different issues with different cloud providers and unexpected limitations that you have to research and deal with, and they're very complex. Cost metering tools, unfortunately, the data layer for them is very usually something like Prometheus, so they don't support very high cardinality like we wanted, and they're usually very FinOps oriented. They're not supporting the forensics needs that we have. And then Cilium and Hubble, perhaps most surprisingly, they're not suitable here, even though they obviously have incredible observability. But actually, this talk is based on a blog post where I go into a lot of details, and there are GitHub issues linked on that topic in the blog post. And the topic being the fact that Cilium fundamentally made a very complex design trade-off where all of its observability related to connections, it falls into one of two buckets. One bucket is either you get volumetric data, bytes and packets with no context, you're not going to know which endpoints and origins the data is going from and to, or you're going to have non-volumetric data with a lot of context. You'll know that this pod is talking to that pod, and maybe you'll even have named port information, but you're not going to know how much data was sent. You're not going to be given the counts of bytes and packets, or within connections, you'll be given something that's called flows in Cilium parlance, which is a loosely defined metric that the definition of which I'm not going to recite to you here, but it's really not relevant to trying to measure something accurately. So for our solution, what did we decide to do? We decided to build something ourselves from the data that's available to us from Linux. We run Cilium everywhere in all three clouds, and we run it in different modes. In some places with kube proxy replacement and in others without. But most importantly, we don't run the tunneling mode. And as long as we don't do that, we actually, from Linux's perspective, there's a raw IP address and port information available because Linux obviously tracks the information with which connections are open to the machine. And we have access to all the data through the contract interface. As you can see here, we have connection information, source port, destination ports in both directions. It's amazing. The only thing we're missing that we need are byte and packet counters, which we can actually enable by using the accounting feature. And we looked at the Linux code for how these counters are implemented. They're just this very simple atomic increments. There's nothing to fear here in terms of the performance hit. We can measure byte and packet throughputs per connection pretty easily. So by accessing this data, we can get all the information we need. So what we built are kubenetmon agents, which are daemon sets running on every node, whether it's running Keeper or ClickHouse or something else. They're scraping contract every 5 seconds, and they're forwarding connection records to kubenetmon servers over gRPC. And every time they scrape the data, they reset it. So basically, for every connection, the counters are sent as a delta, the current time on the previous scrape. And then kubenetmon server, it looks at the information of the Kubernetes cluster, and it annotates, resolves the endpoints and the IP addresses to individual workloads. And if it's a remote IP address, it tells you where it's located, what cloud, what region, et cetera, et cetera. There are a couple interesting things to point out here. Originally, this was not a hub and spoke architecture, it was flat, but it was very expensive to do attribution in kubenetmon agent. So we moved it to kubenetmon server. And also in server itself, originally we were pulling the Kubernetes API. It's also very expensive, and we started using informers instead. That's much, much more efficient. This data, once accumulated, aggregated, is flushed to Loghouse, which is our deployment of ClickHouse for internal observability. And the cardinality that we can support is massive. ClickHouse lets us support very wide rows. So we have information, the local and remote regions, namespaces, availability zones, nodes, instances, anything you want. And then if the directions for ingress, then if we want to add more, we have a connection flags table, which is a flexible map. We can just add any connection we want. And a cool feature we're using here is we're relying on a table engine called Summon Merge Tree, where we put every single column, except of bytes and packets, into the key by which we sum data. So what I mean here is when we insert rows, we round down the timestamp, insert timestamp to the nearest minute, to the previous minute actually. And then automatically this means that with our 5-second collection period, the data is summed up, the bytes and packets, summed up for every connection on a per minute resolution and automatically just averaged out for us. If we want to have per second rate, we just divide every record by 60 and we get per second rate, and all the jitter, all the sort of inconsistencies you might have with missed scraping intervals due to restart, they're automatically smoothed out. It works very nicely. And if we want high resolution, we just change the granularity to which we round down the insert timestamp, and we get a 5-second, 10-second, anything you want, any kind of resolution you want. Cool. In terms of storage, we don't really have to worry about it because the compression here works incredibly well. So in just one of our regions, we have over the last 90 days of retention, 400 billion rows. That would have cost us in terms of storage 90 terabytes, but in reality, they compress in about 30x to less than 3 terabytes or TB bytes. We're being more accurate, so that's very nice. And with this data, boom, we have the insights that we wanted. We can talk about cross-availability zone traffic. We can zoom into individual pods that are contributing to it too much. If a customer is taking backups to a different region, to a different cloud, constantly we can discover this now and control that behavior. So this is amazing. And this tool, this entire infrastructure was open sourced. We built kubenetmon and we open sourced it and we documented it very well. We published an associated blog post that you're welcome to read. There's very interesting discussion there happening around Cilium. You can read the GitHub issues, and that's about it. So try it out, contribute if you want to. I'm sure it will help some people out there. Thank you.